So what I'm going to do is for the next 40 minutes talk about SIR, epidemic modeling and control problem that we have used to teach process dynamics and control to chemical engineers. Okay, now I've been here in the faculty of chemical engineering program at ASU for 35 years now. I'm in my 36th year. But longer than the time I've been here at ASU, I've also been a MATLAB user. And in fact, I was back when I was working at Shell Development Company in the late 1980s. In 1987, that one of the people in our lab said, "Oh, there's this thing called MATLAB. We should check it out." And so I was assigned to purchase the first MATLAB license for Shell Development Company. Back in 1987, it had only 5 toolboxes and no Simulink, and of course it was very useful then, and it continues to be useful now. I'm very pleased to be able to share this webinar. Now, I would like to acknowledge the students that have been involved in this work: Sarash Banerjee, Mohammed El Mistri, Siyu Shi, and Christopher Cobbs. And then also aspects of this work have been funded by an NSF pandemic preparedness phase 1 project. Okay, so what I plan to do is pretty much describe this problem, give you a background on this problem, because it's essentially a chemical engineering process control problem, even though it deals with a societal problem. Okay, so the connection will be very clear. And how we developed a series of computer modeling assignments for our undergraduate course. Okay, one involving open loop dynamics and then closed loop control using PID control. And then in the graduate class, we reprise what we do in the undergrad course. And then consider model predictive control. Okay. Now everything that I'm going to show is using off-the-shelf MATLAB and Simulink. And in fact, all the files have been shared. I'll talk about that in a minute. And then at the very end, I just want to talk about how we have used the problem in research and beyond. That will just be one slide overview to call attention to some recent publications. Okay, now this is the proper link to the MATLAB file exchange link that has all the files that I will be demonstrating. They work, okay? They worked for me. They worked on MATLAB Online, and maybe the speed of the webinar might not allow you to follow along. If you can follow along. That's fine. Otherwise, you have it all available for you. The file exchange also has a folder with documents that has documents that I will refer to. Okay, and then just make sure that you work inside the PID and MPC control materials folder, because you get the file gets put in the file exchange and then you have to actually go into that folder. One thing that I will mention is that this happens to be the very first time I've posted something on file exchange. And then I had a question for Aiken, and then I put the wrong link on the chat. So forgive me for that, because I was trying to see how I could edit some of the description. But everything is available for you to use, okay? So 461, our undergraduate process control course in the chemical engineering program, is a typical course for chemical engineers who usually have just a single controls course. It's required for ABIT accreditation in the United States, and we try to go the gamut of topics from open loop dynamic modeling, linearization transfer functions, to control strategies with emphasis on single loop PID control. Sometimes we have a chance to do cascade and combine feedback feed forward, and maybe a little bit of decentralized control. But the key emphasis on making sure that we can do single loop PID tuning. And in our case at ASU, we rely on internal model control tuning, okay, and for the PID controller part, and as a way of getting systematic tuning rules, as a way of understanding inherent requirements to control, and and that's a big part of the class. And in fact, the tuning rule that I will show in this talk is systematically obtained based on the dynamics of the system. And then for those who have gone through 461 and want to know more, there's an advanced process control class. And here we have chemical engineers as well as students from other disciplines. We'll get some electrical engineers, some mechanical engineers that will join the course. Now, I will mention one thing on with respect to what George indicated, and he talked about the different interest of control engineers in terms of the topics that they work on. I would say that in a process control class, we're usually focused on conservation of mass and energy and species accounting, which relates to reactors. And we're not so much doing momentum conservation and problems that relate to that. And that defines a lot of the applications. Now, when the pandemic hit back in in spring of 2020, and as we considered then teaching the course in the fall, myself and many other people in the control community were thinking, well, what could we do to use control skills to deal with the pandemic and epidemic modeling? So there's a big resurgence in looking at epidemic models, and in our case, the susceptible infected infectious recovered, or SIR acronym, is a very classic epidemic system. And so we were thinking, well, how could we use this effectively? Now, some considerations is that we still wanted to make this a chemical engineering course, keep it as a chemical engineering course, relate to chemical engineering principles. So this was important to have that perspective. And then also a concern that the classical SIR problem, where you start with a population that is that has no infection, and then you go and the infection progresses, that may not be a suitable problem, because you basically don't have a nice steady state to begin with, and where do you linearize from, and a whole bunch of issues, and that could be a problem. So as myself and Siyu Shi, that I mentioned earlier, was one of the first students to get involved with this, and then Mohammed El-Misri back in fall 2020, we came upon this great paper by Professor Corey Simon, who's a professor at Oregon State Chemical Engineering Program. And it's an open access paper on the SIR dynamics as chemical reaction kinetics problem. And what he notes here in this paper, in one of the he treats it as a special case, but when you have births and deaths in your model, you actually have two steady states, of which one is an endemic state condition, an endemic steady state that has non-zero infection. Okay, so that turned out to be a charm for us, because then that gave us conditions for a nominal steady state over which we could get a linear model, and then we could see how our control strategies would work on that. Okay, so so this now is the problem, the epidemic problem as a chemical reactor. Okay, and basically it's a continuous stirred tank reactor. You have births and deaths, and then you have four reactions. Okay, one related to infection, right? And where you have this beta parameter, and then this relates to proximity or distance. It's affected by masking, lockdowns. It's going to influence how people get infected. And then you have recovery, which can be aided by treatments, Paxlovid or the like. You can have vaccination, which can take susceptibles into the recovered population. And we added, as we have learned with COVID pandemic, that there can be loss of immunity and possibility for reinfection. So all these four phenomena enter into the problem. And for the initial consideration, for the treatment in the undergraduate course, we are interested in manipulating this beta and treating these other variables as disturbances or exogenous changes. Okay, so again, as I mentioned, there's two steady states, of which the endemic one is the most interesting, and it's going to be the basis for the for linearizing our system. Now, we're teaching students about dynamic modeling, and you do the species accounting. And by the way, if you go into one of my handouts that's in the documents part, you'll see my derivation of the of this model, where you have basically two states for susceptible and infected. We have four outputs that we can, so there's two states. There's the one manipulated variable that you're going to be seeing consistently, and then you have these disturbances. By the way, in the multivariable problem that I will be discussing at the end for MPC, we will make vaccination a manipulated variable, and then we consider four outputs. In this case, the SIR populations, and then the rate of infection. You could add more outputs if you wanted to. One of the things I'll mention now, and it'll become clear, there's many variations that you can do on this problem, and you're all welcome to try your own, and as you see what I'm going to develop. Okay, so the first part of the project is to look at the linearized system. And again, my handout includes the linearized equations. And then here we're able to evaluate the linearized transfer function models, both numerically with respect to the endemic steady state, and also using the symbolic math toolbox. Okay, and I will illustrate this. There's actually in the files that I made available, there's 4 live scripts and 3 Simulink files. Okay, that comprise so 3 of the live scripts rely on a Simulink file on top of that. And one of the things that was very remarkable for us in working on this problem is that, as you see in the highlighted salmon colored box here, was that the poles are a complicated expression. This is a simple problem that can have a lot of sophistication, but the zeros can be sort of understood pretty much by inspection, right? And it turns out that the transfer function that relates the beta, right, the transmission rate, to the infected population, that's going to be our main transfer function for designing the controller, is actually a second order with left half plane 0 transfer function over all operating conditions. So that was fascinating for us. We knew it would have a fixed dimension, but the fact that it would always be a left half plane 0 makes things so much simpler when we do the IMC later on. And again, you can sort of students, when they evaluate this, can see numerically their coefficients, and can see that the system's overdamped. You can also play around with the model parameters and create conditions that are underdamped. It's always open loop stable, so you can get a lot of understanding. Okay, and let me just I can go quickly here, and in the interest of time, I may not be able to show the all the live scripts working as much as I would like, but everything works. That's my guarantee. Okay, so here's our live script where we define the parameters for the problem. We have the linearized model, and then we can get the transfer functions. We can get step responses for it, and then we can also get the symbolic representation. Okay, so that is all nice and neat, and students can, again, it's all nice and interactive, so we can play around with the different transfer function inputs, see responses now for the linearized model. Yeah, you can also play around with the different. This makes things more infectious. This makes it less infectious. Okay, and so clearly MATLAB and this is all off the shelf, provides a very helpful computational tool. Okay. Now, okay, so let me just let's leave it like that. And so now the next step would be to evaluate then the linear versus the nonlinear responses. And here we can build a Simulink window, and students can effectively go from the first principles model to building the Simulink model for the nonlinear case, and then they have the linearized model to contrast against. And by the way, the structure will be common for pretty much everything that I will show. Okay, and this here again is illustrating. Now you can run the LiveScript, and you can contrast nonlinear to linearized model for different magnitudes of the inputs involved. Get insights, get intuition about the problem, right? So and again, if we went to that LiveScript, let me see, let's close this here. So we go to the okay, so here's the open loop webinar. Okay, and then again, this LiveScript pretty much like the other one has many features. So the other one, then it calls Simulink window. DE are my initials, and I ask students to always personalize their models. And again, you sort of run and you get the plots that you saw me show before. You can add some more. I mean, I have them look at the infection rate just for fun. You can add other outputs to the system. Okay, and so yeah, so okay, so let's so basically as students write up this this assignment, they want they're asked to discuss how do the responses agree with physical intuition. Again, we're all living through the pandemic, so there should be some relationship to that experience with to the actually what we're seeing in the computational model, and then the usefulness of the transfer functions and understanding the dynamics of the system, getting then a sense also, well, how useful is this model? What deficiencies does it have? And assumptions, but then could it still be useful? Could it still inform decisions by public health officials, the general public? Okay. Now, that's for the open loop part. Now we want to do some closed loop control. We like IMC, and basically it's a Q parametrization. Again, the time involved does not allow us to go into detail on internal model control, but it's been around for a long time, and the basis is you doing a Q parametrization to design a controller. And then it was established again many years ago. It was actually one of my first papers that I co-authored with Professor Manfred Murari and Sigrid Skogestad, that for many problems of interest, models of interest, the Q parametrization leads to a PID controller type. Okay, and we teach that to the students. It's a good way also of understanding inherent model requirements, or model features that impact control. There's a lot of benefits. Now, in the papers that I've attached and some other materials, I describe how we do the derivation of this tuning rule that's used for this problem. Again, remember, we have this second order system with left half plane 0 over all operating conditions, which makes us very happy. We apply the IMC design procedure, work it all into its classical feedback equivalent, and get ourselves a model-based tuning rule that's for a PID controller with filter, and that has the model parameters and then the lambda adjustable parameter for speed of response, hence the term lambda tuning. That's used a lot in industry. Okay, and we want to also tune separately for set point tracking and disturbance rejection, and we can do that by basically making once we we can specify different lambdas, and then we can rearrange that into a classical feedback system with a pre-filter. And so we have a lambda for set point tracking, a lambda for disturbance rejection, and hence the 2 degree of freedom. Okay, so here again, now students have built this open loop model before and are happy with it and have played around and understand it. Now it's time to put some control around it. So we evaluate basically the same PID tuning to both the linearized model and the nonlinear model. We do allow for a stochastic disturbance, which is something I'm not going to talk about in the presentation, but you can see that in the papers, and it's in the functionality of the live script. And then you can see here the pre-filter, okay, and just want to point out, the PID block is the standard PID block that's off the shelf from MATLAB, and you have to use the ideal form. And again, when the students now go and try out the closed loop control, it's always good to see something bad to contrast with something good, right? And so here's a bad result. Okay, now this is bringing, and again, the nominal operating conditions are up here at the initial steady state, and this controller is trying to achieve a 90% reduction in the infected population. It only has 1 degree of freedom, okay, because we set the lambdas equal, and this, even though it reduces the infected population a lot, it creates a lot of lockdown variations. These are the things we don't like, and we have lived through them. And by the way, there's different inputs here. When I show the live script in a minute, we'll be able to see the inputs for improved treatment, vaccination, and then reinfection. Okay, so one thing that I like to highlight to students as I'm teaching this on this topic is that we always focus on the control variable, but the manipulated variable is just as important, right, for in control problems. And in this, it is certainly in what relates to a problem as this one that has societal implications, the nature of the manipulated variable response is critically important to performance. Okay, so this is now by adjusting the lambdas, and here setting the set point lambda to be slower, the disturbance lambda to be faster, you can see that this is a lot nicer. Okay, yes, we have to restrict, take measures to reduce infection, but then with improved treatment, vaccination, we can get back to the way things were before. And then if there is some reinfection, loss of immunity, then the beta has to be changed. Okay, and you can see that again, best to sort of look at this with the live script. And again, my apologies because because of time, I can't go through. Let me close my calendar here. Okay, let's see. So now we have the PID. Okay, so everything follows as if we look at the live script. Okay, it's got all the information as before. It's got all the sliders for interactivity, not the linearized model. Here you have now the transfer function of interest and the parameters for the linearized model. You have the lambdas that you can adjust, the tuning rule, built-in tuning rule, and then you call your Simulink file, and then So see here, I have the good case, and then you can see here more completely the different changes that occur. Remember that in this single input treatment, these are all considered as disturbances. So we have just one manipulated variable. Here you have your tuning. You even get a little bit of integral squared error if that's something that you like. So lots and lots of information, and this is what I said was good. I can take it back to the bad, which was, I think, what was it? Was it one and one, a single degree of freedom. Needless to say, when this is provided to the students are given a template, they build a program, they're given certain responses that they can, so that they can check their program and make sure it's okay. And let's see, let's run this again. And yeah, so you can see, yeah, you can see this is the bad one. Okay, but if you go ahead and just increase your lambda here and make this one a little bit smaller. Again, the interactivity offers a possibility for students to play around with things. It doesn't take that long. It's pretty fast, even on the MATLAB Online. So it's a great experience for students to deal with an interesting societal problem. Okay, under okay, and this should let me see. Sometimes it's you can always clear the output and then just try it again. It should yeah. So so far so good. Okay, so okay. So they have to write things up again. And in fact, you know, what we've been doing is sort of, we will, you know, have students answer certain questions. They can even do it on the live script, and they can submit a PDF of the live script, and that can be graded. So we ask similar questions as before, in both looking at the comparison between the linear and nonlinear, how to adjust the PID controller for best performance, and then return to the question of deficiencies in the model, now in the closed loop sense, and assumptions, and how could this be a useful computational model with a closed loop strategy. Okay, so yeah, actually, let me continue. I don't know where. Yeah, so much for the undergraduate class. And this is actually, they have 4 computer modeling assignments, so this is 2 of the computer modeling assignments required in the class. In the advanced process control course, now we can we reprise some of the PID IMC tuning and model-based tuning for PID controllers, but then we also talk about model predictive control and multivariable control. Okay, so now, and by the way, in the treatment that we had before, we've kept it continuous. Yes, it could be made discrete and whatnot, but we pretty much reserve the discrete time sample data treatment to the MPC case. Okay, now again, time does not allow me to provide a detailed discussion of MPC, and I'm assuming that many of you are acquainted with this, but this moving horizon picture representation here is standard to MPC, and we have a prediction horizon. We have a set of moves that get computed in the future. We can include forecasts of signals if they are available. We have weights attached to solving this problem, and in fact, I'll show here one objective function, right, where we're basically solving for a set of moves over a horizon. We implement the first one and do the receding or moving horizon treatment, and we have weights associated with keeping the control variable at set point. And then also a move suppression weight, right, down here below, where we penalize the changes in moves. But we also have the possibility of setting a target on a manipulated variable. And in a problem like this one, then subject to constraints on inputs and outputs. So in a problem as I have been describing, okay, and you think about, well, we have here the infected population we're trying to keep at a set point, and we have, yes, the beta, But hey, we have these things that we call disturbances, and one of them, the vaccination, you could say, hey, maybe we can add that as a manipulated variable. So now you have two manipulated variables, one controlled variable. Well, maybe we can set a target to one of the manipulated variables. Maybe we can set a target to the beta, that and see how we can then play off on the problem. So we have a lot of tuning parameters. It's a fiddler's paradise. And I've been learning as I learn more and more about MATLAB. There's things like Simulink design optimization and all sorts of things that you can do to try to learn about how to tune those design variables better. But in this class, we get to just see them, evaluate them, play around with them, right? So in the MPC problem, unlike the PID problem where I have already a couple conference papers, I haven't written this one up for an educational venue, but I hope to do that soon. So what I have enclosed in the documents is the description of the exercise as is given to students. So you have two manipulated variables, okay? Beta and vaccination rate. You're still worried about the keeping that infected population at set point, the removal recovery rate constant, and the loss of immunity reinfection parameters, which are time varying. Here it says that they're constants, but they can change over time. They represent unmeasured disturbances. You can make something a measured disturbance if you want to. It is a digital controller with daily sampling, and then you have the ability to. And in fact, in this particular problem formulation, we try to give a target to the beta. It is, and try to see if we can take it to its own set point, and then there's constraints on the problem with respect to rate of change and the like, and. Here, we're using everything is off the shelf. This is the MPC block from the MPC toolbox. Nothing custom here. We're building on the models that we had before. Okay, and then we also allow for testing on the stochastic conditions and let students explore that, right? And here again, and I will, illustrate this in a second. I'll just, I'll show some results, and then we'll go to the live script and see if we can play around with this. Okay, this is the result that comes up when you first run the live script and in its current conditions, and you look at this and it's like, okay, well, we lowered that infected population. That's great, but there's a lot of oscillations here. Here's the beta, which may not look too bad, but look at the vaccination. It's not a lot of vaccination. It's sort of oscillating a fair amount. So the first thing that comes to mind is let's put a little bit of move suppression on that vaccination. And then, we could set beta to a target. Right now, it doesn't have a target, but we could set it. In fact, I might, we could do a little bit more vaccination. We could set beta back to where we started, right? If beta is related to distancing, masking, restrictions, and, we'd like to go back, if that was possible, to go back to pre-pandemic world, then maybe, I don't know, how could we, manipulate this to do that? And then how could a treatment improvements with infections? Again, it's a very nice computational model that we can play around with. So if we go ahead then and increase the move suppression, set a target for beta, you can see here that now it's nicer. Those oscillations are sort of gone. Here I've actually put a constraint on 10% increase. Okay, here we return the beta. In fact, the beta actually even gets better than pre for a short period of time. But here, wow, it used a lot of vaccination. In fact, this vaccination constant is a percentage of susceptibles. And as we know, vaccinations are very controversial. Some people may like them, some people don't. There's resource. So as a computational model, we can explore that. And in fact, one of the things that we ask students is to maybe just have a restriction of what percentage of the susceptible population can be vaccinated and see what kind of trade-offs do you get and the like. Okay. So, let's then go to what would be our final live script. Let me see how we're doing time wise. Okay, so yes, here we have this is the MPC one, and I let me show the MPC. This was the one that I showed before, and this is just the off the shelf block. I mean, the same block with the same parameters. This is based on the linearized model. This is just applied on a nonlinear system. And then this is applied on the linear system. And, you can add things. You can go in here. See, this is how we added a target for the manipulated variable. Okay, you could also add a measured disturbance. You can do a lot of stuff. And I think that's one of the beauties of being able to use a commercial tool like MATLAB in a classroom environment, is that even these problems that are essentially, I mean, they look simple, but then there's a lot of sophistication that you can get from exploring them, and a lot of questions that students can answer. And so let's go to let's see, where is the webinar? Yeah. So then here as again, now you're getting used to everything being very consistent with respect to the modeling, linearized model. Now you have prediction horizon, move horizon, the infected weight, the move suppressions, the target for the beta, and then the weight that you give to trying to meet that beta objective, and then the restrictions on vaccination and the like. So we can go here and let's see how, let's just run it. Even this one doesn't take that long. Just hope it cooperates with me. Yeah. So then here, what was it that I mentioned before? Well, let's add some move suppression. I personally am not a super fan of move suppression, just because it's so weight and it can be a little arbitrary, but it's what's involved in the treatment of. So this is one here. Let's make this a little higher. Let's make this, I don't know, about 500. The lambdas are great because they relate to closed loop time constants, right? Speed of response. But this is just a weight on an objective function, and you sort of have to play around with it. So let us see. Yeah. So then this now, yep. So now you can see how everything is better looking. I must have had a higher one before to get the plot that I showed before. Oh yeah, I also had I also wanted to see here. I've gotten rid of some of the oscillations. I don't have a lot of vaccination. So then let's go ahead and add. See, the target for the initial beta is to go back to the original. You could go to half, you could go to 75%. But let's put a weight on it so that the controller will start dealing with it. Okay. And then yeah. So hopefully here we will see. Yep. So we get the response as before. And okay. Should come up. Yes, you can see. And then if you're like, well, this is too much vaccination for whatever reason, we can just say, well, let's limit it to maybe like 30%. I don't know. I'm just doing this on the fly. And it may very well be that when we do this, see, the problem that we end up having now when we limit the vaccination and we still want that beta target is we now have this offset. So maybe we don't want to weight that as much. And we can, students can play around with that, okay? That you get the picture, right? So, okay. So let me then wrap up the talk by so again, I just giving you a very brief sense And my timer is going to go off here in a second. So let me. Okay. Yep. So beyond the classes, in the research, in the lab, we're very much interested in data-driven, predictive control relevant identification, and these things now are done on MATLAB, Simulink, and we also use CPLEX, and this is not again not all off the shelf. This has been things that we've developed, and I just call your attention to these recent papers from the lab. You just go to my Google Scholar and you can access these that show our 3 degree of freedom predictive controller, which is sort of tunable like IMC. Also, this model on demand framework that allows us to handle nonlinear systems. By the way, we have a number of people in the lab that are finishing, are out on the job market. They are students that know how to solve problems, and they are the reason for these efforts and the successes in this work. Okay, so to wrap things up, hopefully I've made my case that we can use the SIR epidemic model as a process control model or system to explain process control concepts. I've already mentioned multiple times that even though it's a simple system, it does offer a lot of sophistication, and these computational tools, which I've shared with you, can be very helpful. And of course, I would say that there's many opportunities and avenues for exploration and problems to be solved. And maybe among the attendees, maybe there's a lot of alternatives that you could think of or ways of modifying. If you do, then make sure you acknowledge us, and in terms of giving you some inspiration for your efforts. Okay, so that's pretty much it.